Hello brothers and sisters. Today we're going to implement Mamba in less than 5 minutes. Mamba is one of the leading competitors to transformer models, which are the base model architecture for transformers, Llama models, GPT-3, 2, 4, and basically every big language model that you have heard of has been using transformers. But Mamba is a new type of recurrent neural network that essentially uses SSMs, or selective state space modeling, and SSS, which is selective state spaces, which are essentially recurrent neural networks. So we're going to be implementing this graph right here, this architecture. The flow is kind of simple. We have an input tensor. This is going to be routed to two projections. Here we have a convolution. Here we have a nonlinearity, which is a sigmoid in this case. And then this is also a sigmoid, I think. These are just activations. We pass this side through an SSM, which is the selective state space model they outline in the paper. Then they have a multiplication here, where they multiply the output of the SSM with this variable. And then you have a final linear projection, and that's pretty much it. So let's begin. First, we're going to import torch, tensor, and a couple of things here. So from Zeta, we're going to import the SSM, and that's pretty much it. So let's get started. We're going to call this model Cobra. So this is a Cobra block. I'm just going to put dim and some of these other parameters. So we have to figure out what parameters exactly SSM takes. So it's going to be the rank. These are different parameters than transformers. So we have the dim in features, DT rank, dim inner, and D states. So here we're going to create a projection. So we're going to say just project equals the it really should be dim. So let's change that to dim. Then what activation are we going to? Oh, yeah, we have a convolution. There's just going to be a convolution of 1D. And that's pretty much it. Activation is going to be, is that the ReLU symbol? I keep forgetting which one it is. I forget what this is. Let's just use swish. Or, yeah, silo. So we have silo here, and we're going to initialize, and that's pretty much it. So here we have the tensor, and we are just gonna create two pathways. So we're gonna call that X. Actually, first we're gonna create a residual, then split up the paths. So we're gonna have X, X1, which is going to just project the inputs, then X2, And so these are now splits. Now we're going to apply the convolution to the first one. We might need to debug the convolution after, but apply the activation. Oh, we forgot to initialize our SSM. And yeah, that's pretty much it. Then we're going to apply the swish. We're going to apply the SSM now. One thing I've learned after programming for so long is that you can never really expect something to work. So just like expecting something to work is not going to get you anywhere. I'm going to be completely honest. This is a continuous process that you have to constantly debug. You should never expect something to work. It's quite, it's quite sad, but don't ever expect anything to work, and you'll succeed. You'll be a good engineer. So here we're going to apply multiplication, and then we're going to add the skid connection for gradient flow, and then we're going to apply a projection and then get an out. Now let's see how this works. If this works, then we can move on into building the model. Let's see. Again, don't ever expect anything to work in programming. It probably isn't. You have to always expect errors. Always expect errors, and you'll never be caught off guard. Most people, just run code and thinks it's going to work, but the universe is not something we can fully control at the moment. So there will always be things that are outside of our sphere of control, and there's no way to really catch them. We have to just accept. We have to just debug stuff. So there's a bug here. We need to debug the shape. One of the biggest problems in machine learning is just aligning the shapes of tensors. It's one of the biggest problems. It's the most frequent problem you're going to find. So here, this is how you print the shape. So you get tensor, and then the shape, and then, that's basically that. So there's an error. So what's the error? So, okay, the way we initialize this is incorrect. What is it? 256 DT rank. Let's try again. So the dimension is always going to be the last here. Okay, so now that's good. So we have passed the we have passed the projections, the initial projections, but as I said, there's going to be a problem with the convolutions. So let's debug those. Let's debug that. So yeah, you see, so the projections are good. The convolution is what is not good. Convolutions are hard because they have a lot of parameters. Let's see. Yeah, look how many parameters that is. It's honestly quite hard to remember all this. But we're going to fix it. I forgot how to do this. Let's see if that works. I'm just going to ask ChatGPT for now. So basically what we're trying to do is create a convolution in 1D that outputs. We're trying to create a convolution that essentially outputs the same shape of the. We're trying to get a convolution that outputs the same shape as the input tensor. So I see. So we need to get the inner right. So it's called the in channels here is the middle part. And so let's see. That's why this wasn't working. In channels, out channels. Let's see. I think it's working. Yeah. The size of a tensor 64 must match the size of a tensor. Um, I see. The bug is now in. Bug is now in the Cobra there. yeah, so kernel size 1, 1, 1. Okay. Oh, look at that, it works. Cool. Okay, so now we're ready for the next process, which is actually transforming this into a model that you can use. Here you go. Here we are. Let's go. We're just going to copy this, and we're going to initialize some stuff here. But we're also going to initialize the num tokens and the depth. And that's pretty much it. So text. So here we have a new module in Zeta called text token embedding. So basically we just put the dimension, the number of tokens, and whether or not we want to use L2 norm embed, in which we do. So then we're going to also create the layers. I'm just going to do that and add some positional arguments. And we're also going to initialize a norm for good luck. So again, norms, what they do is they basically just radically increase token stability. So when you're training, it just generally adds much more stability when you're training. So the model actually trains and doesn't blow up its own gradients. And so you can norm before, after embedding. You can norm after the layers, and I'd recommend all of them, to be completely honest. And that's pretty much it. Let's give it a quick go here to see, and let's see if that works. I see. There's a problem. So let's fix that. That is not an issue with the code that I'm writing now. That is an issue with code from earlier. And so now we have fully implemented this architecture here. Basically, two projections, we split them up, convolution, activation. Still not giving in, is it? I see. Try again. So we have an input. Projected, we create two paths. Then we have a convolution. Then we have an activation, and they also have an activation. We apply the SSM, and we multiply the output of the other path, and then we apply another projection. And that's basically Mamba. Now what really matters here is, okay, I haven't updated my Zeta correctly. So that's pretty much it. basically what we did here is we created the first block. We created just one of this. We initialized some stuff here. We initialized the projection, convolution, activation, the SSM, and then we did the forward pass. Create the residual, split up the paths, apply the convolution, apply the activation, apply the SSM, apply the activation for the other path, map mul, add the skip connection, and project the output. And then now what we're doing is we're looping. This is the main class. We're initializing the same variables, but we have the number of tokens, the def, and we're initializing the text token embedding. Hopefully it works. If not, I have a couple things to fix. Layers, norm, and then first we're embedding the tokens. We're taking text, which are integers, and we're transforming them into tensors. We're embedding them, then we're normalizing them, then we're looping through the layers. For layer and self-layer, we're looped through the layers. Okay, so that is not working out. So, okay, after we loop through the layers, then we apply a norm, and that's pretty much it. An example of forward pass for this would be x, which is a random integer of 10,000, and then 1 in the sequence length. Then, okay, so this isn't working. We're just going to go the traditional route. Which is just embedding number of tokens and then the dim. So that's pretty much it. We initialize some variables, we initialize a random integer, and then we just run it. That's pretty much it. That's how you implement Mamba from scratch. Maybe we went over 5 minutes, but generally pretty simple. Just initialize some projections, convolution, activation, SSM, and that's pretty much it. And then you just put that in a loop however many times you want. Yeah, look at that. Fully functional now. Check out the output shape. Would you look at that? Those are probabilities. So yeah, that's pretty much it. Let me know if you enjoyed this, and join the Agora Discord and check out Zeta if you want to build models super easily. We're trying to make the simplest neural network framework of all time, so you could easily build neural nets like this. We made a tutorial on vision transformers that you can check out on YouTube. We made a tutorial on vision transformers and how to make a language model in 5 minutes, also using Zeta and PyTorch. So just check out these videos and yeah, stay tuned. Join the Discord. We have a Discord where we've implemented more than 400 models in the past year. We're a research lab called Agora, and our mission is to democratize open source multimodality AI research. So the next video in this series is going to be the Vision Mamba and Simba paper. Very, very good papers, very good models, very quickly approaching state of the art, if not beating them in certain cases. And yeah, we'll be exploring those architectures next, so stay subscribed and stay tuned. Thanks for your time.